Tantor Audio presents Hidden in Plain Sight, the simple link between relativity and quantum mechanics, by Andrew Thomas, narrated by Tom Zingarelli. Universe. Noun. 1. The universe is one thing, the only thing that exists. Preface. For the last 7 years, I have been running a website on fundamental physics, www.whatisreality.co.uk. I am pleased to say that over that period, the website has grown to become one of the most popular physics sites on the web. The 7 years working on the site have provided me with the opportunity to consider some of the most challenging questions about fundamental reality. Some avenues, which initially appeared promising, turned out to be blind alleys, while other seemingly innocuous principles turned out to be surprisingly fruitful. This audiobook presents some of the most important insights I gained over those 7 years. I am pleased to say the website has gained high praise from some of the most famous names in physics, but I have been more heartened by some of the comments left by casual visitors to my site, especially those who have appreciated the site and felt I managed to make physics exciting, entertaining, and easy to understand. Hopefully this book can continue that trend. Andrew Thomas. Hidden in Plain Sight Book @gmail.com. Swansea, UK, 2012. I now have a Twitter account on which I will post updates, @AndrewThomas101. 1. Unification. In our modern world, we have grown used to ever-increasing complexity. We perpetually have to upgrade our mobile phones to the latest version 5.0 with new features we never knew we wanted. We have to buy the latest television with hard disk recording built in and a baffling remote control to match. It feels like it is just a matter of time before the Internet becomes so complicated that it develops self-awareness, calls itself Skynet, and launches a thermonuclear war against humanity. Complexity is seen as a virtue, a selling point. Extra features are seen as a good thing. Are you not confused enough yet? I want to strip my life back to simplicity. I have canceled my Facebook account. I have organized my apartment, stripped it down to the basics, and discarded all unwanted junk. By removing distractions, I hope it is going to allow me to concentrate. When you feel the complexities of life are getting you down, you have to strip your life back to simplicity. We tend to think of simple things as more beautiful. They are more economical, with less waste, less superfluous clutter. If we clear our heads, we can see things more clearly. If we clear our heads, we can see the truth. Nature also likes simplicity. Nature abhors waste, both in materials and in energy. Everything in nature is done for a good reason. We see beauty in simplicity because we can see its underlying efficiency. We might recoil from seeing an ostentatious sofa because so much of its covering serves no purpose, the inefficiency of its design being antithetical to the beauty of nature. However, when we see a sleek, lean, minimally designed chair, we are instantly attracted to its Spartan beauty, perhaps until we have to sit on it for a couple of hours. Due to nature's close affinity with simplicity, the advance of fundamental physics over the centuries could be seen very much as the pursuit of simplicity. As physics has progressed, it has been found that more elegant, simpler theories have been found to be the best match for reality. It is very important to remember this when we do physics. Ask yourself, are you making things simpler? If not, then think again. As Albert Einstein said, any intelligent fool can make things bigger and more complex. It takes a touch of genius and a lot of courage to move in the opposite direction. In physics, one of the most successful ways of simplifying our explanations has been by reducing redundancy in those explanations. If we find we have two theories which explain two apparently different behaviors of nature, we might find it possible to replace both those theories with a single theory which still manages to explain both of those behaviors. When this happens, the process is called unification. The resultant unified theory will be simpler than either of the two previous theories, as it reveals a deeper underlying truth. This process of unification always represents a landmark in physics. It is like drawing a line in the sand. It shows we have reached a new level of understanding. We will never have to go back to our previous level of ignorance. Unification is, in many ways, the ultimate goal of physics. If physics is ever to provide a complete understanding of the universe, then the last act which will be performed by the very final physicist will be an act of unification. This book has a single goal, though it is highly ambitious. The aim of this book is to reveal a link, possibly a unification, between relativity and quantum mechanics at the deepest possible level, the fundamental level. This link is based on an extremely simple principle, a simple idea. Simplicity is good. I like simplicity. What unifies unifications? As we start out on our quest, a good starting point might be to examine some of the major unifications in the history of physics. Maybe we can detect trends or similarities in their approach. Maybe we could adopt aspects of their approaches to aid our quest. With this in mind, what follows is an historical review of some of the major unifications in physics. Don't worry too much about following the details. Any principles which are important for our discussion will be described in later detail in the book. For the time being, just get a feel for the history of unification. We start in 1638, when Galileo, the man described as the father of modern science, published his Discourse on Two New Sciences. Galileo realized that if you are traveling at a constant speed in a constant direction, for example, being a passenger on a steady train, you feel as if you are stationary. Galileo had the insight that it was fundamentally impossible to distinguish the two situations of moving and being stationary. To be precise, Galileo stated that there was no experiment you could possibly perform which could detect if you were stationary or moving at a constant velocity. This unification of being stationary and moving stands as the first of the great unifications in physics. In 1665, a 22-year-old Isaac Newton wondered if the force which pulled apples from a tree was the same force which held planets in orbit. Again, we see a simple, brilliant insight, an imaginative leap. From Newton's clear vision, a description of the force of gravity emerged as the unifying theory for two behaviors which were previously considered to be unrelated. Another unification occurred in the 19th century by the man widely acknowledged to have been the greatest experimental physicist of all time. In 1831, at London's Royal Institution, Michael Faraday demonstrated that if you push a magnet through a coil of wire, an electric current flows. Conversely, if you pass an electric current through a wire, it can deflect a nearby magnetic compass. From this, Faraday deduced that electric currents create magnetic fields, and moving magnetic fields create electric currents. Thus was electromagnetism discovered, unifying electricity and magnetism. However, Faraday was no mathematician, and he lacked the mathematical language to describe his discovery. The next unification was revealed by the Scottish physicist James Clerk Maxwell, who, unlike Faraday, was a mathematician. Maxwell took Faraday's results and constructed four equations which describe the connection between electric and magnetic fields. Maxwell showed that an electric field would generate a magnetic field, and conversely, a magnetic field would generate an electric field in an oscillatory fashion. The result was a self-sustaining electromagnetic wave which traveled through space. After calculating the speed of this wave, Maxwell found it to be the same as the speed of light, and thus had a brilliant insight. Light is a form of electromagnetic wave. Hence, here was another unification, this time linking the field of optics with electromagnetism. The next series of unifications happened in the 20th century and was supplied by Albert Einstein, whose work we will be considering in detail later in this book. From a young age, Einstein had wondered what would happen if you moved so fast that you caught up with a light beam. It would seem that you would view a stationary wave of light. However, Maxwell's equations seemed to indicate a constant speed of light, regardless of the motion of the observer. Hence, Maxwell's result for the motion of light did not agree with Newton's laws of motion. Einstein managed to combine Maxwell's result with Newton's laws, but only by radically altering our concept of space and time. His resultant special theory of relativity unified not only electromagnetism with mechanics, but also space with time. Also, through his famous formula which arose from special relativity, E equals mc squared, Einstein launched us into the atomic age by unifying mass with energy. Einstein was on a roll at that point, and 10 years later, after a great deal of extremely hard work, Einstein struck again. Einstein had the brilliant insight, which he called the happiest thought of his life, that the force experienced by an observer undergoing constant acceleration was indistinguishable from the force of gravity. This represented another unification, this time between gravity and accelerated motion. Conversely, if an object was in free fall, it would not feel any force of gravity. It would be as if it was floating freely in space. This meant that gravity did not exist as an entity in its own right. Gravity was the curvature of space. Objects traveling in a straight line in curved space appear to be drawn towards the center of curvature, and this is interpreted as the force of gravity. The resultant theory, the general theory of relativity, unified gravity with the geometry of space. The next unification occurred shortly after the discovery of relativity. The newly developed theory of quantum mechanics was not consistent with special relativity, as it only considered particles which moved very slowly compared with the speed of light. In 1927, Paul Dirac combined special relativity and quantum mechanics to create the first quantum field theory. This theory was further refined throughout the 20th century to become the greatest triumph of physics in recent years as the foundation of the standard model of particle physics. The shy Dirac was awarded the Nobel Prize in 1933, and his first instinct was to turn it down as it would generate unwanted publicity for himself, until he was persuaded that turning down the prize would generate a lot more publicity. The last unification to date occurred in the 1960s, when physicists started to consider the symmetry between the particles associated with electromagnetism, the photon, and the weak nuclear force, called the W+, W-, and Z particles. Unification was achieved by importing an idea which was first used in studying the physics of metals and other solids, symmetry breaking. Physicists realized that all four particles would be massless, that is, they were all symmetrical, at high energies, for example, the unimaginably high temperatures reached in the first moments after the Big Bang. However, as the energy decreased and the universe cooled, this symmetry would be broken, and the particles would be free to take different values. The photon was left with no mass, but the W+, W-, and Z particles all collected mass. For this reason, the weak nuclear force can only operate at short ranges and is weak, whereas massless photons can bring us light from the stars. Hence, the two forces of electromagnetism and the weak nuclear force were, in fact, the same force behaving in two different ways at our everyday low energies. If it is sufficiently hot enough, then the electromagnetic force and the weak force would merge into a single force. This was confirmed in the 1980s in CERN, the European Laboratory for Particle Physics, when they recreated the temperature of the early universe and demonstrated the existence of the so-called electroweak force. Considering general themes in all these approaches, one thing our historical study has revealed is that, in general, unification in physics is achieved by a single imaginative idea. This might come from Newton pondering on an apple, or Einstein deciding that you could never catch up with a light beam. Unification always requires one single brilliant insight. Even in the case of the electroweak unification, with many physicists involved, it still required the inspired introduction of the symmetry-breaking concept before unification could be achieved. It does not matter how much money or how many researchers you throw at the problem. Unification is only ever achieved by a moment of inspiration. Unification is definitely not achieved by a design by committee. Also, the ideas by which unification is achieved are generally extremely simple ideas. Anyone could understand these ideas. In fact, we could say that any unifying idea has to be simple. The idea of experiencing no gravity in a lift in free fall or catching up with a light beam are simple ideas which anyone could understand. Similarly, Newton's idea connecting a falling apple with a planet held in orbit is a simple concept. It was as if these great unifiers picked up on something which was under our noses all the time, something which was missed perhaps because it was too simple. something hidden in plain sight. As Walter Isaacson said in his book Einstein, His Life and Universe, Einstein's approach was typical of his ingenuity. He examined a phenomenon that was so very well known that scientists rarely puzzled about it. Or, as Nobel Prize-winning chemist Albert Szent-Györgyi said, scientific discovery consists of seeing what everyone else has seen, but thinking what no one else has thought. The process of unification could be equated to a tree, with each theory being a leaf on the end of a twig. As we move back down the twig, we eventually get to a junction point between two twigs, a point of unification. As we move further down, twigs merge into branches and the branches merge into the trunk. As we continue to move further and further down the tree, we find the number of branches gradually reduces as the process of unification reduces the number or redundant branches, theories. With each step, with each unification, our model of nature becomes simpler. But what will we find at the base of the tree? What is holding up the entire structure? As our progress down the tree has seen our model and our theories getting simpler, you would expect that at the ultimate base of nature we will surely find a principle which is simple, beautiful, and elegant. As the great physicist John Wheeler said, "To my mind there must be at the bottom of it all not an equation, but an utterly simple idea. And to me that idea, when we finally discover it, will be so compelling, so inevitable, that we will say to one another, 'Oh, how beautiful! How could it have been otherwise?'" Relativity and quantum mechanics. The quest for one particular unification is dominating current research. As we enter the 21st century, we find the same two theories have dominated physics for 100 years, the theories of general relativity and quantum mechanics. Both theories have been astonishingly successful and have been tested to remarkable accuracy. General relativity is our best theory of gravity, accurately describing the motions of planets, stars, and galaxies, and has correctly predicted the existence of black holes. Quantum mechanics is the force behind the laser and the transistor, and is therefore the force behind the computer revolution. Quantum mechanics is generally regarded as the most successful theory in the history of science. Nobody argues with either theory. They are both undoubtedly correct. The only problem is they have absolutely nothing in common. General relativity is the theory of big stuff, describing the motion of planets and galaxies. Quantum mechanics is the theory of little stuff, describing the behavior of subatomic particles. For the most part, physicists only have to use one or other of these theories, depending on the scale of their subject. For example, in order to study the motion of galaxies, they would use general relativity. In order to study the behavior of particles, they would use quantum mechanics. So, because of the differences in the domain of application, this method of switching between the two theories, though not ideal, works perfectly well for most purposes. However, we are interested in the quest to uncover the fundamental truth of nature, and nature surely does not use one theory for small objects and another theory for big objects. As far as nature is concerned, objects are objects. The laws of physics apply equally to all objects. So at a deeper level, there must be a more elegant theory which applies to all objects, regardless of their size. It is the unearthing of this deeper theory, combining general relativity with quantum mechanics, which is the focus of much current research. Einstein's theory of general relativity revealed that the very fabric of space itself can be curved in the presence of mass or energy. In the absence of mass or energy, space is flat, it is uniform and without features. However, in the presence of mass or energy, the fabric of space is curved. This is a wonderful sweeping theory. One can imagine vast tracts of space being bent in a beautiful, smooth curve by a planet or star, like an interstellar ocean wave. And just like an ocean wave, this glorious curve of space keeps moving and curving as the planets and stars are constantly in motion. But what exactly is happening at the microscopic level during this curvature of space, when we zoom in to examine this curvature in detail? In the microscopic world, quantum mechanics takes over. Quantum mechanics predicts seething randomness at such small levels, with particles flashing into existence before their rapid annihilation. The resultant effervescent substance resembles foam rather than smooth space, and was given the name space-time foam by John Wheeler. Theories which attempt to unify general relativity with quantum mechanics at this small scale are called theories of quantum gravity. String theory and loop quantum gravity. The two main approaches to finding a model of quantum gravity are string theory and loop quantum gravity. These two approaches are opposites in many ways. Loop quantum gravity emerges from general relativity. String theory has a closer connection to quantum mechanics, but very similar in one important way. Both string theory and loop quantum gravity are based on the principle that the best way to analyze nature is to discover the structure of the smallest components of reality. String theory was first proposed by Yoichiro Nambu in 1970 while at the University of Chicago. When first introduced, the theory had more modest goals than it has now. The theory has been considerably expanded over the years, but the fundamental principles have been retained. String theory considers particles as being composed of microscopic strings, closed string or open string. As a closed string moves through space and time, it sweeps out the shape of a cylinder. These cylinder shapes can simplify our understanding of the interactions between particles. The shape of this interaction between elementary particles can then be viewed as a single string cylinder pinching itself and separating into two string cylinders. The great attraction for theorists is that this stringy cylinder eliminates the infinities associated in dealing with the interactions of point particles. As we take successive snapshots in time, cross-sections through the string cylinder appear as microscopic loops which join and split in a smooth manner. If these microscopic loops are sufficiently small, they can appear just like point particles. So the apparent interaction of point particles could actually be the splitting and joining of microscopic string loops. Just as a guitar string can vibrate in many different ways to produce different notes, so can a loop of string have different modes of vibration to produce different types of particles. For a loop, a whole number of vibrations must fit around the string. Higher notes require more energy, so the particles would have greater mass. In this way, different particles, such as electrons and quarks, are just different vibrations of one of these tiny loops of string. Much is made of the fact that string theory predicts a particle which appears to have the characteristics of the particle which is expected to carry the gravitational field. Even though such a particle has never been detected experimentally, it has already been given a name, the graviton. Such a particle would have to treat all objects in the same way, just as gravity is an attractive force for all objects. The fact that such a particle emerges naturally from string theory is often taken to mean that in string theory, gravity comes free. String theory's prediction of gravitons is one of the main selling points of the approach. This all sounds well and good, until you realize that string theory makes another prediction which is not so welcome, the prediction that space should have 10 or 11 dimensions. This is a blow, as we only see 3 spatial dimensions and 1 time dimension. This has forced the ingenuity of string theorists to come to the fore, as ways of tucking up the extra dimensions into exotic structures have been suggested. However, having to resort to these kind of techniques is not really what you want in your simple fundamental theory. String theory is almost the only game in town when it comes to current theories of quantum gravity. However, there is one more proposal being worked on by a smaller community of researchers. Loop quantum gravity attempts to unify quantum mechanics and general relativity by applying the standard technique of quantization to Einstein's equations for general relativity. The key figures in this field are Lee Smolin of the Perimeter Institute near Toronto, Carlo Rovelli of the University of the Mediterranean in Marseille, and Alpay Ashketar of Pennsylvania State University. We will be hearing some of these names throughout this book. Loop quantum gravity's initial aims were less ambitious than those of string theory, being purely a theory of quantum gravity with no attempt being made to predict the properties of elementary particles. However, this has changed in the latest version of the theory, which now does indeed predict the elementary particles. So the latest version of the theory is, like string theory, presented as a fully fledged theory of everything. The main prediction of the theory is that space is not continuous, but is instead quantized into discrete chunks, atoms of space. These chunks are the smallest possible units of volume, each approximately 10 to the negative 99 cubic centimeters. Neither of the approaches of string theory nor loop quantum gravity seems to be enjoying unqualified success at the moment, with progress being slow on all fronts. String theory has been getting a bad press as the theory which makes no testable predictions. Loop quantum gravity, however, boldly proposed a testable prediction that high-energy photons should travel slightly slower than low-energy photons, and this difference becomes measurable over long distances. However, in 2009, a gamma-ray burst from deep space was analyzed and no speed difference could be detected. There is a certain competitiveness/animosity between researchers in these two distinct fields, both groups being convinced of the correctness of their approach and the failings of the other approach. Such competitiveness should be healthy in theory, but it has not appeared to work out that way. This is not a golden age for physics. A personal criticism of mine, which applies to both string theory and loop quantum gravity, is that neither theory has anything to say about the foundational problems of quantum mechanics. The foundational problems raise questions about the nature of reality at a very low level, before it is even observed. It is hard to even imagine what form reality takes before it is observed, so this might be considered more of a philosophical question by most scientists, and is sadly ignored by researchers. But it is still a problem at the very heart of reality which urgently requires a solution. We will be considering the foundational problems in Chapter 6, which is dedicated to the question of quantum reality. No matter how long they are ignored, the foundational problems will not go away and will have to be tackled at some point. One of the proposals of this book is that a true linkage of quantum mechanics and relativity can only be properly achieved by obtaining a greater understanding of the foundational level. The problem with structure. It was the Greek philosopher Democritus who first suggested that matter might be composed of indivisible atoms, meaning uncuttable in Greek. Democritus believed the properties of the atoms were determined by their shape, so water atoms were smooth and slippery, whereas iron atoms had hooks to bond closely together. His views might sound misguided, but on the basis of what we now know about chemical bonding, it is actually a remarkably good analogy to reality. Throughout the 19th century, successive experiments appeared to confirm the atomic nature of matter until it became an accepted fact. But were the particles truly indivisible? In 1897, the physicist J.J. Thomson discovered the electron, revealing that there were smaller particles within the atom. In 1909, Ernest Rutherford directed alpha radiation at some thin gold foil and found it was deflected. Rutherford interpreted this result as showing that there was a solid, positively charged nucleus at the center of every atom surrounded by negative charged electrons. The continuing division of particles continued through the 20th century with the discovery that protons and neutrons were each composed of three particles called quarks. Even though quarks are considered to be elementary particles, if history teaches us anything, it is that particles which were once considered indivisible later reveal themselves to be composed of even more fundamental particles. In answer to the question, what is a particle? Researchers in string theory would say elementary particles are actually composed of incredibly tiny strings, with average size of about a millionth of a billionth of a billionth of a billionth of a centimeter, called the Planck length. But this has just pushed the question of what is a particle further back. We are now left with the question, what is a string? We seem no nearer our goal in determining the ultimate bedrock foundation of reality. In fact, this raises a potential weakness in all theories which believe nature's secrets can be fully unlocked simply by examining the structure of the universe at increasingly smaller scales. The problem is, surely this drilling could just go on to infinity. How could it ever end? How would we ever know when we had reached the bedrock foundation of reality? As string theorist Brian Greene says in The Elegant Universe, another possibility, should strings fail to be the final theory, is that they are one more layer in the cosmic onion. Whatever structures we end up with, surely we will always be able to ask the question, what is it made of? There is a famous, undoubtedly apocryphal story which circulates in physics circles. A lecturer was presenting a lecture on astronomy. At the end of the lecture, a little old lady got up and said, "What you have told us is rubbish. The world is really supported on the back of a giant turtle." The lecturer gave a superior smile before replying, "What is the turtle standing on?"
Sample complete. Ready to continue?